These are the answers to the chemical bonding practice quiz. Number 1. For each compound below, indicate whether the bond type is likely to be ionic or covalent. So if we see a metal and a nonmetal, then that would be ionic bonding. And if we see two or more nonmetals, that would be covalent bonding. So our first example is COF3. That is cobalt and fluorine. So that's a metal-nonmetal combination, which would be ionic bonding. Our next example is CCl4. That would be carbon and chlorine, which are both nonmetals, so that's covalent bonding. Our next example is P4S3, and that is phosphorus and sulfur, both nonmetals, so covalent. And finally, MnBr2, that's manganese and bromine, metal, nonmetal, so ionic bonding. Number 2 says, calcium and oxygen react to form the compound calcium oxide. Which of the following best describes the bonding in this compound? So calcium is a metal, oxygen is a nonmetal, so therefore this is ionic bonding. Calcium is +2, which means that calcium loses 2 electrons to form a stable ion, and oxygen is -2, so oxygen gains 2 electrons to form a stable ion. That means that electrons are transferred from the calcium, which loses electrons, to the oxygen, which gains electrons. So it's not about sharing electrons, it's about transferring electrons from the calcium to the oxygen. Correct answer is C. In number 3, it says below is a representation of a portion of a crystal of lithium chloride, LiCl. Identify the ions in the representation by writing the appropriate formulas, Li+ or Cl- in the boxes below. So we can see that the box on the left is pointing to the larger ion, the ion with the larger size, and the box on the right is pointing to the smaller ion, the ion with a smaller size. Let's compare the size of Li+ and Cl-. So here's lithium, which normally has 3 electrons as an atom. It has a +1 charge, which means that lithium loses 1 electron to form a stable ion. So the Li+ ion has 2 electrons. The Cl atom has 17 electrons and it gains 1 electron, has a -1 charge. That means that the Cl- ion has 18 electrons. So in terms of which ion is larger in size, 2 versus 18, it's the Cl- that would be larger in size. And so therefore the Cl- is the larger ion and the Li+ is the smaller ion. Number 4 says, which of the following statements describes the electrical conductivity associated with LiCl and provides the correct justification? So we know that LiCl is an ionic compound. Let's take a look at the conductivity of both ionic and covalent compounds. Covalent compounds consist of neutral molecules, not ions. Covalent compounds do not conduct electricity in any phase, whether they're in the solid phase, whether they are melted, or aqueous, dissolved in water. In this video, sugar molecules have been melted, and we're going to test for conductivity.
When wires connected to a light bulb and battery are placed into sugar melted on a hot plate, the bulb does not light. Molten sugar does not conduct electricity.
So again, sugar does not conduct electricity because it is covalent and consists of molecules. There are no ions or charged particles. Now let's take a look at the conductivity of ionic compounds. Ionic compounds do contain positive and negative ions, but in the solid form, the ions are locked in the rigid crystal lattice. So solid ionic compounds do not conduct electricity.
When wires connected to a battery and light bulb are placed into granular sodium chloride, the bulb does not light. It does not conduct.
But when an ionic compound is melted or dissolved in water, it does conduct electricity because now the ions are free to move around. So here is what happens when you check for conductivity with an ionic compound dissolved in water.
Aqueous sodium chloride lights the bulb brightly. Sodium chloride is a strong electrolyte.
So now we have these four choices. Choice A, solid LiCl does not conduct electricity because it consists of neutral LiCl molecules. No, there's no molecules. It does contain ions, but it's because the ions are locked in the rigid crystal lattice and are not able to move and flow. So the correct answer is not A. Choice B says solid LiCl does conduct electricity because it contains Li, which is a metal. So solid LiCl does not conduct electricity because the ions are not free to move around. Choice C talks about lithium chloride dissolved in water. Aqueous LiCl does conduct electricity, or says does not conduct electricity. So again, correct answer is not C, because aqueous LiCl does conduct electricity because now the positive and negative ions are able to move and flow. Again, correct answer is D. Number 5. Which of the following substances can conduct electricity? Select all that apply. Well, we see various compounds. Let's take a look at whether these elements in the compounds are metals or nonmetals. So we see magnesium, chlorine, carbon, hydrogen, oxygen, sodium, and again, another example of carbon and oxygen. So magnesium is a metal, chlorine is a nonmetal, carbon, hydrogen, and oxygen are all nonmetals. Sodium is a metal, so the compounds that contain sodium and magnesium will be ionic, but compounds that only contain carbon, hydrogen, and oxygen will be covalent. So our first example is magnesium chloride, MgCl2. In the solid phase, this ionic compound does not conduct electricity because the ions are not able to move around. The next example, C2H6O, is covalent because all those elements are nonmetals, so it will not conduct electricity no matter what phase of matter it's in. In a similar example, C6H12O6 is also covalent, again does not conduct electricity in any phase. And then finally we have sodium carbonate, Na2CO3, that is ionic, and it will conduct electricity if it's dissolved in water. So aqueous Na2CO3 is a conductor. That was the only choice among these four choices that can conduct electricity. All right, number 6, fill in the missing information in the table below. We are looking at 5 different ionic compounds, and we can tell that these are ionic because they have a metal and a nonmetal. So the first thing that I'm going to do is fill in the symbol and charge for the cations and the anions, and then we can take a look at the correct chemical formula. All right, starting with aluminum selenide. So that contains the element aluminum, which has a charge of +3, and selenium, which has a charge of -2. So there's the symbol and charge of those ions. Next example is magnesium oxide, which contains magnesium +2, oxygen -2. So there's those symbols and charges of those ions. Potassium sulfide is next. Potassium is +1, sulfur is -2. So we have symbol and charges for those ions. Next one is nickel, which they're telling us with the Roman numeral has a charge of +2, and chlorine. So there's nickel. It has a charge of +2 because of the Roman numeral, and chlorine would be -1. So there's the symbol and charges of those ions. And then finally, barium nitride, that's barium +2 and nitrogen -3. So now that we know the symbol and charges of all of these ions in these 5 compounds, let's take a look at the chemical formula. Starting with aluminum selenide, if I have a +3 and a -2, then the only way to get the charges to equal 0 is I need 2 aluminum ions for a total charge of +6, and 3 selenium ions for a total charge of -6. So the correct formula is Al2Se3. Our next example is magnesium oxide, and since the magnitude of the charge on magnesium and oxygen is actually the same, the +2 and the -2, the total charge is 0, so the formula is simply MgO. In our next example, we have potassium sulfide. So since I have potassium +1 and sulfide -2, I need 2 potassium ions for every 1 sulfur to get the charges to cancel out and equal 0, so the chemical formula is K2S. Our next example is nickel, Roman numeral 2, chloride. Since the charge on nickel is +2 and the charge on chloride is -1, I need 2 chlorides for every 1 nickel 2+ ion. So the correct chemical formula for this compound is NiCl2. And then now we have barium nitride. So I have a +2 for barium, a -3 for nitride. In order to get the charges to balance, I'm going to need a total of 3 barium ions for a +6 and 2 nitride ions for a -6. The correct chemical formula is Ba3N2. All right, in number 7, it says fill in the missing information in the table below, but now instead of writing the correct chemical formula for an ionic compound, we just have to supply the name of the compound. And because the way we name an ionic compound is cation first and anion second, we have these 2 columns, and we'll just go ahead and put in the name of each ion. For the first ion, the cation, there's not going to be any change in the spelling. So if the element is sodium, we just say sodium. But for the negative ion, the anion, we change the spelling. So phosphorus becomes phosphide as a monoatomic ion. For the next example, that's copper. Since copper is a transition metal and can have more than one possible charge, we have to put a Roman numeral in the name. So to figure out the charge on copper, we have to know the charge on sulfur. Since sulfur has a charge of -2, that means that copper will have a charge of +2. There is a 1-to-1 ratio between copper and sulfur in this compound, so each sulfur is worth -2, each copper is worth +2. So copper Roman numeral 2 is how we name that, since copper is a transition metal. The sulfur becomes sulfide, so that's the name of that compound, copper 2 sulfide. In our next example, we have calcium and fluorine, so we name calcium just simply as the name of the element. But fluorine becomes fluoride, and calcium fluoride is how we name that. Now, iron is also a transition metal, so the charge on iron is going to be determined by the formula and the charge on Br, bromine. Bromine is -1, and there are 3 of them in this formula. So 3 bromides will be a total charge of -3, and there's 1 iron. So the iron has a charge of +3 to balance the charge on the 3 bromides. Iron with a +3 charge, so iron Roman numeral 3, and then again, that's bromine becomes bromide. So iron 3 bromide. Finally, we have lithium and oxygen. So it's going to be lithium, and then oxygen becomes oxide. So these are the chemical names for these 5 ionic compounds. Number 8, fill in the missing information in the table below. Now we are going to have to supply symbol and charge of cation and anion in which there may be a polyatomic ion present in this formula. So in the previous examples, they were monoatomic ions. So now we see polyatomic ions. And so what I've put on this slide on the margins on the left side and the right side are the names and symbols for the polyatomic ions from that song that I taught you. So again, there's OH is hydroxide, ClO3 chlorate. Their charges are both -1 like NO3 nitrate. Carbonate is CO3 chromate CrO4. Their charges are both -2 like sulfate SO4. And then there's the NH4 plus 1, and then the phosphate is PO4, charges -3. So again, those 8 polyatomic ions may be featured in this table. All right, starting with aluminum and hydroxide. Based on where you find aluminum on the periodic table, its charge is +3. And again, hydroxide is one of those polyatomic ions that you should memorize, OH -1. In our next example, we have copper, which is Cu. It has a charge of +2 because of the Roman numeral. And chlorate is another example of a polyatomic ion that you should memorize, ClO3 -1. Magnesium, because of where you find it on the periodic table in group 2, it is +2. And carbonate is a polyatomic ion you should memorize, CO3 2-. Ammonium is another polyatomic ion you should know, as well as phosphate. So ammonium happens to be NH4 plus 1, and phosphate happens to be PO4 -3. Potassium is in group 1. The symbol is K and the charge is +1. Chromate is one of the polyatomic ions you should memorize, CrO4 -2. There's ammonium again, NH4 plus 1, and sulfate is a polyatomic ion you should memorize, SO4 -2. Calcium is located in group 2. It has a charge of +2, so Ca 2+. And then nitrate is a polyatomic ion you should memorize, NO3 -1. So now that we know the symbol and charge for both ions, let's put these formulas together to write the correct chemical formula for each of these 7 compounds. Starting with aluminum hydroxide, we have a +3 aluminum and we have a -1 hydroxide. So therefore, to get the charges to balance, we need 3 hydroxides for every 1 aluminum. Since OH is a polyatomic ion, we're going to wrap the OH in parentheses and then put the 3 on the outside of the parentheses, like that. All right, our next example is copper Roman numeral 2 chlorate. So we need, for every 1 copper ion, we need 2 chlorate ions to balance the charge. So there are 2 chlorate ions, ClO3 inside parentheses with a 2 on the outside. Cu parentheses ClO3 2, just like that. Now we have magnesium and carbonate, but because the magnitude of charge on the magnesium is the same as the magnitude of charge on the carbonate, we can simply write MgCO3. No parentheses and no extra numbers or subscripts are needed. This is ammonium phosphate. Ammonium is +1 and phosphate is -3. So to get the charges to balance out, we will need 3 ammonium ions for every 1 phosphate ion. Therefore, we'll wrap parentheses around the NH4 and put a 3 on the outside, followed by the phosphate formula, which is PO4. So inside parentheses NH4, outside parentheses 3, and then PO4. Our next example is potassium chromate. So since potassium is +1 and chromate is -2, we need 2 potassium ions for every 1 chromate ion. We don't need parentheses. It would just be simply written as K2CrO4. And then ammonium sulfate, we need 2 ammoniums for every 1 sulfate in order to get the charges to balance out. So parentheses around the ammonium with a 2 on the outside, followed by SO4. So NH4 inside parentheses, 2, SO4. And then calcium nitrate. For every 1 calcium, we need 2 nitrate ions. So after the Ca, it's going to be NO3 inside parentheses with a 2 on the outside. So Ca parentheses NO3, 2. All right, so those are the symbols and charges for all of the ions and the correct chemical formulas. All right, in number 9, we are switching over to covalent bonding, and we have to write the correct Lewis electron dot structure for each of these 3 molecules. We have CS2, SO3, and SiF4. The instructions include making sure that each atom has access to a full valence shell, that we represent the bonding electron pairs with a solid line. If we have to use a double or a triple bond, we would use 2 or 3 lines as needed. All of the non-bonding electron pairs will be written as dots. And in the box, we're going to write the total number of valence electrons for each molecule. So let's start with CS2. We have 1 carbon and 2 sulfurs. Each carbon is 4 valence electrons. Each sulfur is 6 valence electrons, so 4 plus 6 plus 6 is 16. Let's connect the atoms, putting the carbon in the center. So there's our skeleton. And we've already used up 4 electrons in drawing the 2 dashes, the bonding pairs of electrons. So we have to get to 16. So right now we have 4 electrons. Let's satisfy the octet around each of the sulfurs. So this would be a total of 6 electrons, 8, 10, 12, 14, 16. So now I've used up all my electrons. I've satisfied the octet for both sulfur atoms, but the carbon only has access to 4 electrons right now. And since I can't add any more electrons to this structure, I already have 16 electrons total, I'm going to move a pair of electrons from the sulfur to create a double bond. And then I will take a pair of electrons from the other sulfur on the other side and make a double bond. So now each atom has access to a full valence shell. Each carbon, each sulfur has access to 8 electrons. So that is my final answer. All right, moving on to the SO3 molecule. We have sulfur and oxygen. We have 1 sulfur and 3 oxygens. So each of those atoms has 6 valence electrons. So it's going to be 6 plus 6 plus 6 plus 6. That's a total of 24 electrons, valence electrons. For my skeleton, I'm going to put the sulfur in the middle and connect it to 3 oxygen atoms. And in doing that skeleton, I have now used up 6 electrons in drawing the 3 dashes. Now I'm going to satisfy the octets for the oxygen atoms around the edges of the molecule. And we'll see what happens in terms of our total number of electrons. So right now it's going to be 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I was able to give each oxygen a full valence shell, but the sulfur only has access to 6 valence electrons right now in those 3 bonds. Since I can't add any more electrons, I've already reached my total of 24, I'm going to have to make a double bond. It doesn't really matter which oxygen I use, but I have to take a pair of electrons from the oxygen and move it to create a double bond. So I'm going to do that right here. I'm going to move that pair of electrons from the oxygen to create a double bond. Now, each of the 4 atoms has access to a complete full valence shell, an octet. So that structure is done. Moving on to the SiF4, we have silicon and fluorine. So 1 silicon and 4 fluorine atoms. Silicon has 4 valence electrons. Fluorine has 7. So 4 times 7 is 28. plus the 4 electrons for the silicon, that's a grand total of 32 valence electrons. For my skeleton, I will put the silicon in the middle and connect it to the 4 fluorine atoms, like this. And having done that, I have already used up 8 electrons by drawing those 4 bonding pairs, those 4 bonds. So that would be 8 electrons right now. The silicon does have access to a complete full valence shell, but let me go ahead and satisfy the octets for each of the 4 fluorine atoms. So I'm at 8 right now. This would be 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I've used up exactly the right number of valence electrons. Each atom has access to a complete full valence shell, an octet, so that structure is done. Now, in number 10, we have to name these 3 compounds, CS2, SO3, and SiF4. So to use the correct chemical name, we use prefixes for covalent compounds. We don't use prefixes for ionic compounds. So to use a prefix for a covalent compound, the first element is carbon, the second element is sulfur. We don't change the name of the carbon, so it's just carbon, and then the prefix di means 2. We do change the ending of the second element with IDE at the end. This would be carbon disulfide. In a similar pattern, we have a sulfur and an oxygen. So it's going to be sulfur using the prefix for 3, which is tri, and then oxygen becomes oxide. So sulfur trioxide. And then now we have silicon and fluorine, and the prefix for 4 is tetra. So it's going to be silicon tetrafluoride. All right, this is our last question on the chemical bonding practice quiz, and for each of these boxes we have to count the valence electrons, we have to fill in the bonding electron pairs with solid lines, and then if we have to make double bonds we can change that if we need to, and then using the dots for the electron pairs. So I'm going to start with the count of valence electrons. The skeleton has already been given to me. I know I have 1 carbon, 2 chlorines, and 1 oxygen. So it's going to be 4 for carbon, plus 6 for the oxygen, that would be 10, and then 2 chlorines, that would be 7 plus 7 is 14. So 10 plus 14 is 24. Let's go ahead and connect them. So I've now used up 6 electrons in drawing those 3 covalent bonds. And then I'll satisfy all of the octets around the edges of this molecule. So the chlorine and the oxygen atoms will get an octet. And we'll see how many electrons we have. So right now this is 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I have just used exactly 24 electrons. I can't add any more electrons to this structure. The chlorine on both sides, each chlorine has an octet. Oxygen has an octet, but unfortunately the carbon right now does not have an octet. The carbon only has access to 6 electrons. And since I can't add any more electrons, I have to make a double bond. Now I'm going to choose to make a double bond between carbon and oxygen, and that's because oxygen normally forms 2 bonds. So my choice would be to move a pair of electrons from the oxygen and create a double bond. So that's my final answer. If you had made a double bond between carbon and one of the chlorines, that would also be considered correct. At this point, we haven't learned about this phenomenon known as formal charge to decide which structure is more preferred. So I'm telling you that this is my answer, but again, if you had made a double bond between the carbon and the chlorine, I would also have marked that correct. All right, moving on to our next molecule, which contains 2 sulfurs and 2 bromine atoms. So each sulfur has 6 valence electrons, and each bromine has 7. So 6 plus 6 is 12, 7 plus 7 is 14, and 12 plus 14 is 26. Let's connect these atoms, and then let's satisfy the octets on the bromines. So right now that would be 6 electrons that I have used so far in drawing these 3 dashes. So 8, 10, 12. So that bromine is done. 14, 16, 18. That bromine is done. Now I've only used 18 electrons. I still have 8 more electrons that I can add, so I can go ahead and keep satisfying the octets on those sulfurs. So again, right now I'm at 18. This would be 20, 22, 24, 26. So unlike the last example, I don't have to make double bonds because I had enough electrons to satisfy the octet of all 4 atoms, so that structure is complete. Our next molecule contains 2 carbons and 4 fluorines. Each carbon has 4 valence electrons, so 4 plus 4 is 8, and each fluorine has 7 valence electrons, and we have 4 of them. So 7 times 4 is 28. 28 plus 8 is 36. Let's go ahead and connect them with single bonds to start. So I have now used up 2, 4, 6, 8, 10 electrons so far. Let's satisfy all of the octets for the fluorine, and we'll see what we have in terms of total electrons. So right now it's 2, 4, 6, 8, 10. This would be 12, 14, 16. So that fluorine is done. 18, 20, 22, 24, 26, 28, 30, 32, 34. So I still have 2 more electrons left, but if I stick it on one of the carbons, then the other carbon does not have access to an octet. So the only way I can satisfy the octets for both carbons at the same time is to create a double bond, because right now that carbon on the right only has access to 6 electrons, so I'm going to move that pair of electrons on the carbon to create a double bond. Now, that structure is complete because each atom has access to a full valence shell. All right, here's our next set of molecules. So starting on the left, we have Se, selenium, and then 2 fluorine atoms. So the selenium has 6 valence electrons. The fluorine has 7, so 6 plus 7 plus 7 should be a total of 20 valence electrons. I'm going to connect them with single bonds. So I have now used up 4 electrons in drawing those 2 dashes. We're trying to get to 20. So that's 4 right now. Let me go ahead and satisfy the octets on the fluorine, and we'll see what we have. So again, I have 4 so far. This would be 6, 8, 10. So that fluorine is done. 12, 14, 16. That fluorine is done. I still have 4 more electrons to add. I will put them on the selenium. So this would be 18, 20. So I've now reached my total of 20 electrons. Each atom has access to a full valence shell. So that molecule is complete. No double bonds were needed. All right, I have 1 sulfur and 2 oxygens in our next molecule. So each sulfur and each oxygen would be 6. So 6 plus 6 plus 6 is 18 valence electrons. Here's my connection between the atoms. I've now used up 4 electrons in drawing those 2 dashes. Let's satisfy the octets for oxygen, and we'll see what we have left. So right now I'm at 4. This would be 6, 8, 10. So that oxygen is done. 12, 14, 16. That oxygen has a full octet. I'm at 16 electrons right now, so I only have 2 more electrons left. I will stick them on the sulfur, and I'm close, but not quite there. The sulfur does not have a complete octet. Right now, the sulfur only has access to 6 electrons. I'm going to have to make a double bond on one side, not on both sides, just on one side. It doesn't matter which pair of electrons you choose as far as on the oxygen or the other oxygen. Don't take electrons off the sulfur. Take electrons off the oxygen, because if you move electrons from the sulfur to make a double bond, you still won't have a complete octet, and then you'll give the oxygen more than an octet. So I'm going to choose to take a pair of electrons off of the oxygen on the left. And once I do that and move that pair of electrons to create a double bond, this is what I get. So there is an octet for each of these 3 atoms. So that structure is now complete. All right, our next example is HCN. That would be 1 for hydrogen plus 4 for carbon plus 5 for nitrogen. 1 plus 4 plus 5 is 10. With 10 valence electrons, let me go ahead and draw my dashes. So that's 2 electrons for each dash. I've used up 4 electrons so far. I'm not going to put any dots around the hydrogen because hydrogen only needs to have access to 2 electrons to achieve a full valence shell. Let me put dots around the nitrogen and we'll see what happens. So right now I'm at 4 valence electrons total. 6, 8, 10. So I've just run out of electrons, and while the nitrogen does have a full valence shell, the carbon doesn't. The carbon only has 4 electrons right now in this structure. So I'm going to make a double bond and see if that helps. I will move a pair of electrons from the nitrogen to the carbon-nitrogen area to make a double bond. I still have 10 electrons. The carbon does not have a complete octet right now. It only has access to 6 electrons. So I have to make a triple bond. I'm going to move a pair of electrons again from the nitrogen to that spot in the middle to make a triple bond. And now that I've done that, there's 10 electrons total. Each atom has access to a full valence shell. So that structure is now complete. All right, for our final row of this particular table, we have polyatomic ions. And remember that with a polyatomic ion, if there is a positive charge, you would remove 1 electron. If there's a negative charge, then you would add 1 electron to your total. In our first example, we have CO3, and we have a -2 charge. So we're going to add 2 electrons to our total because of that -2 charge. So I have carbon and oxygen. 1 carbon, 3 oxygens. So that would be 4 for carbon plus 3 oxygens. That would be 3 times 6. 4 plus 18 is 22. And then I get to add 2 more electrons to my total because of the -2 charge. So my grand total is 24. Let's connect the atoms. And let's satisfy the octets for the oxygens, and we'll see what we have. So I've got 24 electrons total. Right now I have used 6 electrons in drawing these 3 dashes. So let's keep going. So right now I have 6. This would be 8, 10, 12. Okay, that oxygen is done. 14, 16, 18. That oxygen is done. 20, 22, 24. So I have just run out of electrons. I was able to satisfy the octet for each of the oxygens, but the carbon right now does not have a complete full valence shell. The carbon only has 6 electrons around it. So I can't add any more electrons. I've already used up 24 electrons. I'm going to make 1 double bond. I'm going to move a pair of electrons from one of the oxygens to make a double bond. And now that I've done that, that structure is complete. Each atom has access to a full valence shell. All right, moving on to the Cn- ion. Carbon is 4. Nitrogen is 5. So again, we have 4 plus 5 as far as valence electrons, plus 1 more for the negative charge. So that would be a total of 10 valence electrons. I'll start with a single bond, and then I'm going to satisfy the carbon. So this would be 2, 4, 6, 8, and then finally 10. I just ran out of electrons, but I was not able to satisfy both octets. Both atoms do not have a complete full valence shell, so I can't really add any more electrons, but I could move a pair of electrons from the carbon to make a double bond, and we'll see what that will do. I'm going to move a pair of electrons from the carbon to make a double bond. So the carbon still has access to 8 electrons. The nitrogen is doing better, but not quite enough. There's only 6 electrons around the nitrogen. So I'm going to have to move a pair of electrons from the carbon to make a triple bond. Again, I'm moving electrons from an atom that already has an octet. I'm not going to move electrons from the nitrogen because it currently does not have access to a complete octet. So you normally take the electrons from an atom that already has a full valence shell. So when I make this triple bond, now each atom has access to 8 electrons, and I have a total of 10 electrons, so that structure is complete. All right, last structure on this particular question, last problem of this chemical bonding practice quiz. We have BrO3 with a charge of -1. So the bromine has 7 valence electrons, the oxygen has 6, and there are 3 of them. So 7 plus 6 times 3 would be 18. So 7 plus 18 is 25. And then I get to add 1 more electron for the negative charge. So that would be 26 valence electrons total. Let's connect them. So I just used 6 electrons in drawing these 3 dashes. And let's satisfy the octets for the oxygens. So right now I'm at 6 total. Let's keep going. 8, 10, 12. Okay, that oxygen is done. 14, 16, 18. That oxygen is done. 20, 22, 24. So unlike the carbonate ion, the CO3 2-, I did not run out of electrons yet. So I don't have to make a double bond. I still have 2 more electrons, and I can put them directly on the bromine. So I've used up exactly 26 electrons. Each atom has access to a full valence shell, an octet, so that structure is complete. Again, since this was the last problem on the chemical bonding practice quiz, this marks the end of the video. I hope that those answers and explanations were helpful. Thanks for watching, and good luck studying for your quiz.